in general, try to solve, let's say a n plus b m equals c.
Assuming they're all co-prime.
Okay, right. If they're not co-prime, well, which all of them? A and B, or A and B and C, or A and C, or B and C? All three?
A and B.
A and B. Okay. Let's look at the set of integers. I think that's a really good point. Look at, let's call this set S. This is the set of integers as n and m range over all integers of an plus bm. We're trying to find the values of n and m for which this thing takes exactly the value c. But let's turn it a little bit on its head. Let's let n and m range and see what values this set S takes. Any ideas what the values are? Will kind of hinted to what the answer will be. Devendra? One value will be the GCD. That is true. Should I give you an example to play with? This is kind of a little sideways to what we were discussing a minute ago, or at least it seems that way at first. For example, should I give you two numbers? What is the set? What is the set of all? I don't know. 32n plus 18m as n and m range over integers. What numbers will you get of the form 32n plus 18m? Want to take a minute and play with it?
That's 2 times c.
Okay, good. Let other people play also. Yeah, I like it. Did everyone hear what Yukong said? Good, I'm glad you didn't all hear because he gave me the answer. That's correct. It's very closely related to what Will said. Let's try to play with it. So as n and m range over the integers, the values 32n plus 18m will range over what values? Okay, so you know the answer, but not what. Good. That means you still have something to think about. You got it?
No, I was saying, what is that? What is it equal to?
That's just a set of integers. So this is, S is a subset of the integers. And the question is, what numbers does the set S hit? And if you know what numbers the set S hits, well, then you can tell whether or not C is among, the question is, when is C, well, C is an element of the integers. When is C an element of S? If you're trying to solve that equation. That's the motivation. Karen, you got it? Okay, what do you think it is?
all multiples of 2.
All multiples of 2. Okay, so that's what Yukong said at first. It's twice the integers, so all multiples of 2. Can we try to see why that's the case? Karen?
And both of them are divisible by 2.
Both of them are divisible by 2.
What you have to be concerned about is that you're only going to get multiples of 4 or only multiples of 16.
Or why does it have to be multiples of a single number? It could be some weird subset of the evens. Yeah, the point is 32 and 18 are both even. And so, so note that 32 and 18 are both even. So certainly in this case, S is a subset of the evens. Why is it exactly? Why is every single even number in there?
If we find a way to write Q as a even number and choose very
Okay.
then that doesn't include the other subset.
Okay. Right. So can we write? So what Dipendra is saying is, if 32n plus 18m is equal to 2 has a solution. If this has a solution, then every even number can be represented. So we have an inclusion in one direction, and now we'll have an inclusion in the other direction, and that will give us the equality. Charles.
Can you explain why the second one is true, the second statement is true?
That's the question. Yes, I haven't explained it at all. Dipendra's statement was, if we can solve this equation with a 2 here, the claim is, then not only the number 2, but every even number is there.
Is that true? Like, if that is equal to 2 as a solution, then the set of all evens is in S. Is that like true?
Well, that's what that's a claim. We need to prove it.
Okay.
What's the argument? So you're trying to get this thing to represent 2 times k for any integer k,
Right.
and you found something that represents 2. Suppose you found integers n and m
Yeah.
that get you 2.
Okay.
So if you multiply both n and m by k,
Okay.
that'll get you
Yeah.
2k.
That makes sense. Thank you.
Yeah, no, that's exactly so. So there are 2 things to do. One is to find 2 as a solution, and the next thing is to show that then from this sort of primordial solution, again, we can build all the solutions. Okay? It's a sideways way of understanding this equation by understanding the values that an plus bn m take to try to solve this original equation, an plus bm equals c. Okay, does that make sense? So first of all, can we solve this equation? Now we're starting to get better at this. So did anybody find a solution? I guess you could divide through by 2, now that we know to do that. So 16n plus 9m is equal to 1. Did anybody find a solution? Again, we're searching. We're just searching so far. We need something very robust so that we're not searching anymore.
Looks like the professions look like perfect square. What can we do?
Oh, that's true. That is an accident. That's a fluke. I don't think there's much we can do with that.
64 and 63.
Okay, wow, we have to go that high, 64 and 63? Oh, 64 is a multiple of 16,
Oh,
and
yeah.
63 is a multiple of 9. So what values of n and m? In other words, okay, so Karen is saying let's divide through by 2. 16n plus 9m is equal to 1. And 64 is 16 times 4. And 9 times 7 will get us 64 minus 63 is equal to 1. Okay? So this equation does have a solution in the integers. So there is a value of nm which gives us 2, namely 32 times 4 plus 18 times negative 7 is equal to 2. And I claim now if you want to find a solution to any even integer, all you do is, Alex, if you want, so now to solve 32n plus 18m is equal to 2k, use nm is equal to
multiple words, like
yep, 4k negative 7k. You just bump both of these up by k, it bumps the solution up by k. And so now we know that we'll hit every even number. So every even number is contained in S. S is only contained in the even numbers. That means this thing is all evens. Cool? Cheek.
So is that the only solution, 4 comma minus 7? Are there any more possibilities to represent n1?
Right. So I'm trying not to get the two things confused, but it is a little bit confusing. The first thing we did was we tried to find all solutions to this equation. So having found one solution, we're not satisfied with that. We want to find all the solutions. We turned that on its head and said, what is the set of values? Never mind which values of n and m give us those values. Just what is the set of values swept out by this expression, 32n plus 18m. The claim is we can get all even numbers. The first observation is we'll only get even numbers, because 32 and 18 are both even. Now, if we can find 2 as a solution, then we'll get every even number as a solution, because we just bump up our value of n and m to that by that multiple. Okay? So what we've done is shown that all of the even numbers are in S. We have not shown what the values of n and m are that give a particular even value. Okay? Let's return to the general setting. So here's this set S, an plus bm, that's a subset of the integers. And it seems like you guys have a pretty good guess as to what S will be in general. So back to S is equal to the set of an plus bm, where n and m run over the integers. Let's call this a theorem. S is equal to any guesses? The GCD, yeah, let's call it D times Z, where D is the GCD of A. So the reason it came out to the evens is because 2 is the greatest common divisor of 32 and 18. Okay? Say it again. The D might not.
So you know which an A plus B is equal to C?
Yes?
So that C might not always be equal to C.
That's right.
So then what do we do?
Then there are no solutions.
Oh,
That's exactly the whole point of this exercise. Yes, so Dipendra asked an excellent question, which is the reason we were motivated to study this set S was to try to solve this equation with C. But if C is not a multiple of D, then what are we doing here? Well, that means there are no solutions, because that's exactly what this exercise is having us learn that this set of values only takes the values and exactly takes the values, which is the GCD of A, B times all integers, any integer multiple of the GCD of A and B. And if C isn't in that set, then the thing on the left never hits the value C. And if C is in that set, then it does hit the value C. And we'll even see from the proof how to find it. Efficiently, not by guessing and checking. Efficiently. Okay. So that's the theorem. Any ideas about how we should go about proving this? How should we get started? Charles.
We can do basically what we did for 32 and 18. We take, say A and B are both divisible by D, so let's say it's maybe C over D is A and then okay.
Say it again. Yeah.
You factor out the D and then
Yeah.
You get that should be equal to 1, right?
Okay. Yes. I like so what you're saying is let's just try to do exactly what we did with our example of 32 and 18. The first thing to notice is one direction is that S must be contained inside the D multiples of Z. So proof in two directions. Proof, so the first claim, claim 1, is that S is contained inside DZ. And this is because for any divisor, if L divides A and L divides B, then L divides AN plus BM. If A is a multiple of L and B is a multiple of L, then any further multiple of A and any further multiple of B, their sum still has L as a divisor. If A is even and B is even, you multiply A by anything, you add it to any multiple of B, you still get an even number. Okay? So if this is always a multiple of D and this is always a multiple of D, you add them together, you have no other choice but to get multiples of D. Now the question is, okay, so hopefully that part's easy. How about in the other direction? If we can get D, then we get everybody. If we can solve the equation with D, if that has a solution, then we get everybody just by scaling. And then we're done. So let's write that down. So claim 2, if AN plus BM equals D has a solution, then DZ is contained in S, which implies S is exactly equal to DZ. If we can solve the equation AN plus BM is equal to D exactly, then if you want to get any integer multiple of D, you just multiply N and M by that integer multiple. If you want to get DK on this side, just replace your solution to D by NK, MK. Does that make sense? And so if we can get every multiple of D to be an S, but S can only be contained inside multiples of D, that proves what we wanted. So the last thing we need is to be able to solve this equation. So how do we solve this equation and how do we do it efficiently? And I think Steph already said the words many, many minutes ago for how to do it, but it's something we haven't fully executed yet. So last step, this is what we've been doing with guess and check, but there should be no guess and check in this step. How to solve an plus bm equals d, where d is the GCD of A and B, and do it efficiently. Any ideas on how to do this? Do you remember what word you said?
Euclidean algorithm?
The Euclidean algorithm. So this is the Euclidean algorithm. This is what we have not discussed yet, and it's something that's extremely fundamental, and once someone shows it to you, it's obvious that it has to work, but it's kind of brilliant. So does anybody know, you guys did Euclidean algorithm maybe in school. You remember how it works? I gave you two numbers, even large numbers. 173 and 215 or something. Here are two numbers. Well,
So, I might be wrong, but we said like 215 is equal to 173 times something plus a remainder.
perfect. Quotients and remainders. Back to grade school. So we do 215 is 173 times a quotient plus a remainder, and the point of the remainder is to be in the range 0 to 173, yeah, or 172. Let's make sure we're getting strictly smaller, right? Okay, so let's call this Q0 R0. Yeah, so 1 and 173 plus 42.
So then you
Gets-
get, so then you set 173 is equal to 42 P1 plus R1.
And R1 needs to be less than
41.
41, and this needs to be less than or equal to 41, strictly less than 42. Okay, Q is equal to what multiple of 173? What multiple of 42 gets us below 173?
Would be 4,
4 looks good.
which would be 168.
168, 173 minus 168. What is it?
Yeah, 5.
5. Perfect. And then, now what?
I is going to be less than.
And then you let 42 equal to
Yes.
5 times something. Yeah.
I is going to be less than 4.
So Q is 8, R2 is 2. Does everybody see what I'm doing? And then what?
8 is equal to 2. Where are we? Sorry, 5 is equal to
There we go. 5 is equal to
2 times
2 times Q3 plus R3.
Yeah, and then Q3 is 2.
And 1. And so 2 is equal to 1 times Q3, Q4 plus R4. I mean, some people just stop once you hit 1. Some people keep going until you get to 0, because you don't know. Sometimes you don't hit 1. So the fact that we've hit 1 tells us that these two numbers are co-prime, that the GCD is 1. What this always recovers is the GCD. So what is Q2? Q4? 2, and R4 is 0, and that means that the previous R, once we hit 0, the previous R is the GCD. That's the Euclidean algorithm. Okay, you remember you did this in grade school. Sound familiar? You could do it again if I gave you two more numbers? Yes, okay. So, so what? Well, this is exactly the algorithm that's going to tell us how to solve this equation. It might not be obvious. But let's unpack what the algorithm is doing in general. Okay? Actually, so knowing that the GCD is 1, let's see if we can figure out how this particular equation, how exactly what we've done now will tell us. See, if we tried to do this by hand, if we tried to solve 173n plus 215m equals 1, gosh, that would be annoying. That would be a massive amount of computation by hand. But actually the solution is staring us in the face because we've already done the Euclidean algorithm, which was not hard. We did it all with bare hands computation. So the question is how? How do we unpack all of this back up into a solution to this original equation? Yeah, well, let me give you 5 minutes to try to play with it. Take 5 minutes and try to figure out how our work here is plenty, without any guess and check, to find a solution to that equation. Karen, do you see what to do?
So, is it something that needs to be proved or just explain it?
We're gonna give a formal proof in a minute of what to do in complete generality. But right now I just want to see if we can get from what we did to a solution to that equation. See if you can figure out what to do. DeBendro gave us a good hint, which was, you see we have this R3, which is 1. 5 was this. If we put this back in here, and we put this back in here, and we put that back in there, we're going to unfold things again until we see an equation that only has a 1 on one end and multiples of 215 and 173 on the other. Take a few minutes, see if you can see how to do it. Talk to your neighbors. Discuss. Argue. The hint is that we're trying to represent 1. Well, here's a representation of 1. It's 2 times 1 is 5 minus 2 times 2. Maybe that's not a good looking proof. You can talk to each other. Look on your neighbor's page. Some of you have it already. Getting anywhere?
I can figure out how to put that.
How to find an answer, or how to verify this computation, or how to prove what?
Oh, well, we're not proving that works.
We're not proving that it works. We're trying to use, we're still in the exploratory phase. How do we use this calculation to find a solution for n and m in this equation? This is the key. This argument is exactly the key. You got it? Okay, how did you do it? Okay, that's great. That's great. You'll talk us through it. Okay, we're running low on time. Let's go through it. So, tell me your name again. Ming. So, what did you do?
So I found that 1 equals to 5 minus 2 times 2.
Yes. So let's take this equation. This equation says that 1 is equal to 5 minus 2 times 2. Does everybody see that? This was 1. Once you hit your GCD, then you put it on one side and you leave it alone. And on the other side, you have whatever we had, 5 minus 2 times 2. Go on.
And for above line is on the 2 equals to 42 minus 5 times 8.
Yes, that 2 came from somewhere. That 2 was the previous remainder. That 2 is this, well, one of the 2's is a cube, but the other 2 is the remainder. So 2 is equal to, so this 2 is 42 minus 5 times 8. 42 minus 5 times 8. Does everybody see that?
Yeah, now we replace it with 5, right?
Now look, we have, let's put the 5's together. So this is a plus 16 5 and one more 5, so that's 17 5's. Did I get that right? Minus 2 times 42. And hopefully that's still a correct statement. 17 times 5 is indeed one more than 2 times 42. 84, 85. 17 times 5 is 85. Yep. Okay. Now what? Well, that 5 came from somewhere. That 5 is 173 minus 42 times 4. 173 minus 4 times 42. That was 5 minus 2 times 42. Does everybody see that? So that was writing 5 as 173 minus 4 times 42. 173 minus 4 times 42 went into 5, and then I have this left over, 2 times 42. Again, let's regroup. How many 42s do we have total? Now there's some arithmetic to do, but it's not guessing. We're never guessing. It's always just completely exact arithmetic. We might be proving this next time. Okay. let's continue. So 1 is equal to, I have 17 times 173, and how many 42s? 17 times 4? How many? Minus 70?
In total.
And 2 more? So 17 times 4, 40 and 28 is 68, and 2 more is minus 70 times 42. And hopefully that's still correct. Now it's outside my ability to compute in real time. And finally, 42 all the way up there was 215 minus 173. So this is 17 times 173 minus 70 times 42, but 42 is 215 minus 173. And so, in the end, we have, so 70 minus 17, 173s, that's what, 60, 57, 53?
No, it's 87.
Oh, it's a plus, thank you. 87, 173s minus 70, 215s, and that is a solution that I hope you agree we would not have guessed in a reasonable amount of time. Sitting there with our fingers trying to find whether 70 multiples of 215 come out to 1 more or less than 87 multiples of 173. And yet we could do it extremely efficiently by running the Euclidean algorithm forwards and then backwards. Alex.
Can you just explain where you got the 17 and the third one?
Here, 17 times 5?
Yeah.
Okay, that happened from the line above, where I had a 5. The 2 we replaced by 42 minus 2 times 5. And then let's group the 5s together. I have a negative 2 times negative 8 5s. So that's a plus 16 5s. And then 1 more 5. That's where that 17 came from. So there's coefficients getting added on top of the equation, and then you work your way all the way back up to the original equation, and that lets you solve this equation. So the Euclidean algorithm is the thing that is the key to unlocking all linear equations in the integers. And it's extremely efficient. It's the only algorithm we have that's efficient. Next time we're going to prove that this process always works, although I think this is a big enough example that hopefully you're convinced. It'll take a little practice,